So we're going to do a little review of what trees are, and we're going to implement one, or at least implement the insert, implement some traversal. There's 3 different traversal types, and then we'll talk about like removing nodes, and then we'll talk about some more deeper concepts with trees. But yeah, just a reminder, trees are a data structure that relies on nodes, similar to a linked list. So each thing that holds data is a node, and each node has a value. So this has a numerical value, and each one of these nodes has a value and a left and a right pointer. And the left and the right pointer will point to other nodes. Since we are doing a binary search tree specifically, can someone remind me why, what's different in a binary search tree versus a regular binary tree?
Your binary search tree should be weighted. So you're gonna always put the greatest numbers to the right.
Mm-hmm. Yeah, that is correct. Versus binary tree is just a tree that has, where each node has at most 2 children, like subnodes. Okay, so we want to implement this. So I'm just going to go to my code here. So from the code that from the scaffolded out code from the assignment a few days ago, this is basically what it looked like. It had a class node, and it also had a class BST. As you saw today with linked lists, there's a few different ways that you can actually structure this. So some people might create a node class and then a BST class, hold on to the root inside of the BST class and do all the functions. Another way is to just kind of create your tree here. So tree equals none to begin with. So it's not pointing to anything. And when I want to actually create this tree, I can start with an insert. So I can do insert, and then you can send in the tree or the root. So this is, let's call it tree root. Tree root. And you can send in the value that you want to insert. So I am going to do it without the BST class. Would someone, does anyone have any objections to that? Or do you want to like actually like really see it with the BST class? I think it makes it like unnecessarily complicated. Not too much. Yeah.
You're driving, do it.
Good. Julio. Okay, so I'm going to remove the class. I'm going to just make these as regular methods. And then these are not going to take self. These are all going to take a root. Okay, so let's see. Actually, yeah, I have an example down here. So when I want to insert, I can just say tree root equals insert, and then I send in the root where I want to start and the value. So that means this insert function is supposed to take in the root, the value, and it's supposed to return the actual tree. So let's get started. How do we make this happen? When we want to insert into a binary tree, so let's say we have an existing binary tree and we want to insert. Actually, let's say we don't have an existing binary tree. So the first insert, what are our cases basically? What do we have to consider when we're trying to insert to a binary tree?
If the root is like none, as in if the root is not already set, and then if it's not set, then we have to set it first, because you can't like go to another level or depth. I forgot what they're called, but you can't go anywhere else. You can't go left or right until you have the root.
Okay, so if root is none, basically set the root to the new node. Okay, I think that sounds good. And then else, what are our cases in the else? So else means that there is an existing tree. What do we have to do with the else?
Compare the value to the root, and that'll decide whether it's left or right.
Okay, so compare val to root val. Then go left or right. Okay. Okay, I think that's a good starting point. So let's go back to the code and get it started. So I'm going to just make a comment here. Comment all this out. Oops. Okay. So we start off, we're taking in a root. So if root equals none, I think none is more proper. Also, we can ask if not root. So these are all equivalent, if not root, if root not none. Or sorry, is none. We can just keep it if root is none. Does that make sense? Then we said, what do we do? We're going to set the root to the new node. So root equals our new node. And I'm going to create the new node up here because I know I'm going to use it. I'm going to have to use it either in here or in the else statement. So I might as well just define it up here. So new node equals node. And I'm going to send in the value that I'm looking for, or that I want to insert. Okay, so it's a top, new node, root equals new node, and then I can return root, and that is it. So then when I'm saying tree root equals insert this, it will, whatever it returns is going to go back into here. So that means I'm going to have a node. Sounds good. So else, does someone want to take over the keyboard and type? Oh, it's okay. Okay, so else we want to compare. So if you guys should, give me what to write. If what?
If the value is greater than the root node value, then you want to check the right side of the tree. If it's less, you'll check the left side of the tree. Are you going to do, will you end up having to do new none statements, checking to see if there's if right equals none, if left equals none, to implement the new value?
Sorry, could you say it one more time?
Yeah, do you have to do another, you might have to do another check if like root dot right equals none, it'll be then root dot right equals value.
Yeah. Yes, I agree. So, okay, so if the value, so we inserted. Let me try to get these to be side by side, just so we can draw. And okay. Move here. Okay. It's just so much easier to see it when we have a tree. Okay, so let's say we have 50. We want to insert this one if the value is greater. So let's say we want to insert 60. So we're checking root dot value, which is here. 60 is greater than 50, so it's going to go in here. So that means we need to set. What are we setting exactly here? So root dot right. Mm-hmm. And then we can say root dot right equals. So I'm not sure if there's anything else that exists over here already. So this is a way of doing this recursively, so you don't have to have a pointer and then like traverse through the entire tree until you find the correct spot to put it. So the way to get around that is to set this root dot right to whatever the insert function returns with starting at the new root. So the new root that we're starting at is going to be root dot right. So we already looked at this root. So we said we know that the value has to be somewhere on this side. So let's say we have a bunch of other, let me do this. So let's say we have this. And I know that 60 is supposed to go somewhere here, but I'm not sure of the values yet, but I'm going to say root dot right is going to be equal to whatever gets returned from the next insert statement. So the new root that I'm going to start at is going to be this one. So this one is going to be denoted by root dot right. Okay, so root dot right. And the value is going to be the same value that we used. So basically, with every recursive iteration, you are starting at a different root. So in the beginning, when we initially called insert, we chose the actual tree root, which is the top. But then when we're inside the insert, we need to keep finding the so this is a tree, this is a subtree. So every top of the node, it's like like a little version of the tree, basically. So every time we call insert, we can just change the root and then say, okay, if we're starting at this root now, where should I insert this value? Should I go left? Should I go right? Is it empty? If it's empty, right? Because we already checked. If it's empty, then I should put my node right here because this is where I want it to be. So let's say we had, let's say this is 55, this is 53, and we are trying to insert a value of 60. So the 60 is going to, we're going to start off up here, right? This is our initial root. We check, it's not empty, so it's going into here, right? So value 60 is larger than the current value, so we are going to target this smaller tree. So now the new insert function is going to call this its root. So we are looking here. We don't care about this part anymore because we know that we're not going to insert in there. So we care, huh? Oh, might have been a mistake. Okay. Okay. But yeah, so we're trying to insert 60. With the new iteration, we look at this tree now. This is the new root. And we look at the root, we look at 60, we're like, okay, is 60 greater than or less than 55? It's greater than. So we are going to want to insert it here. So this is going to trigger this again, right? Value is greater than the root value. So this is the new root. So I'm going to say that root.right, so attached to this side, I want to add something, and I'm going to have to go into my insert function again with this right value. And root.right for this node, for node 55, is going to be what?
None.
None, exactly, because there's nothing there. So when we go into the recursive function a third time, the root value is going to be equal to none, right? So when it's none, it's going to create the new node and set it to that node here, and then return it. So if we returned this new node now gets set to root.right. So this goes back to the 55, right? 55 was the root. 55.right is going to be our new node that we inserted. And then this gets returned, and it gets put to root.right of the 50 node. I know there's a lot of backtracking, but yeah. And the same exact thing will happen for the left side. Questions about this? I know this is a little.
Yes. Quick question. What happens if you're trying to insert, let's say, for example, there's already a value, like when you have to rearrange the branches, like if you're trying to insert, I don't know, 54.
Mhm.
How do you go about rearranging all the
So
nodes?
with a binary search tree, you don't have to care about rearranging. So the rearranging is only with a specific type of tree called an AVL tree, and that is where everything has to stay level. So if you're inserting 54, you get to 55, then you go left because 54 is smaller. When you get to 53, you have to go right because 54 is bigger than 53. So with 54, you're inserting right here, and you don't need to move anything around.
So you don't care if it's balanced or not, you can just continuously add. Okay, got it.
Yeah, exactly. So a caveat of binary search is if the tree is not balanced, then the worst case scenario could be O of n. It could be like everything is just chained like a linked list, and you have to visit all the nodes anyways. So a balanced binary search tree would be, like you said, like when we're adding another one, if we need to rebalance it, it will rebalance. So everything kind of stays within the same height, and you don't have like a bunch of nodes up here and then like one train going down here. Everything kind of stays within the same area. So yeah, I'm going to okay, so root.right. I think we just return root at the end. I know we didn't check for the left side yet, but I want to show, actually there's, okay, let's keep implementing this and then we will print it out because yeah, traversals where we have to talk about. So basically this will work. So just by running through it right now, we know that this way of traversal should work. So else value is less than the root dot value. Oops. I forgot it's LF, not else. There we go. Okay. Then we want to set the root dot left. I know this is a little bit of weird syntax to understand immediately, like what is this actually doing? It's basically saying if I want to modify, if my value is larger than where I'm at, than the current node that I'm at, then I would want to modify my right tree. So that means my right tree is going to change. That is why I say root.right equals whatever this function returns the next time. Same with this left. So now instead of root.right, I'm going to be sending root.left. So we need to explore that side of the tree and then insert the value. We don't really need an else here because else it's the same exact value. And let's say for our purposes, we do not want duplicate values. We don't want to insert a value twice. Okay, let's see. In theory, oops, turn root. Okay, in theory, this should insert everything correctly. If we do, we'll try to build this tree out. What was it? Command Shift, no. What was it that Benjamin was saying that you highlight and Command D? Yeah, there we go.
Command D, yeah.
Perfect. Okay, so it's tree underscore root. There
Maybe
we
I
go.
missed it earlier, but are you accounting for if it equals value?
No, because I don't want to actually insert anything if it equals the same value. So if it's greater than,
Nope,
go this way, if
just
it's
gonna
less
return the
than, go
root.
this way. I guess we can have an else. And this one can just return root. I don't know if this will mess up anything. But we can try. It won't mess up anything here because we don't have, well, this is a duplicate. So we'll test it out in a bit. But yeah, let's do this, see if we get any errors. Okay, seems like it ran, no errors. I'm going to just go into folder itself so I can run it. So okay, cool. Okay, okay, no errors. Good, good. Okay, so how do we actually look at this tree? How do we traverse and see all the nodes that are available inside of it? So there are three main ways to traverse a tree. These are all called depth first search traversals. So depth first means that you're going all the way to the end of the tree, and then you're like kind of backtracking and getting all the rest of the nodes. There's another type of traversal that is common in graphs, sometimes in trees, that is called breadth first search, so BFS. So this one, basically, you will visit the nodes by level. So you look at this node, you see all the neighboring ones. So you have this one and this one. You add these to a queue, and then you start visiting them. So as you visit, I visit this one, I see what else I have, I add those to the queue, and then I visit the next one, I add its stuff to the queue, and then I go through the queue, and then I start visiting all the elements that are in there. So it's pretty much going level by level. That's breadth first search. So starting from this point outwards, like a ring, basically. I know this doesn't help much because it's a smaller one, but say we have this bigger tree. So breadth first search would start here, then it would visit these two nodes, then it would visit these four nodes. Depth first search, which is the more popular one. There are 3 ways to print these out. Printing in order will print the values of your tree in order. Like, since the one over here is the smallest, the one over here is the largest, the way that this prints is going to be this one, then 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 this one, because that is how typically a binary search tree is. Let me see if I have some values. Yeah. So in order, you visit the left, then the parent, then the right. Pre-order, you visit the parent first, and then the left subtree, and then the right subtree. So I'll show you exactly what each of these mean. Post order means that you visit the parent after you visit left and right. So it'll make a little more sense once you see the code, and you will probably remember it more. So let's do this. This is also another recursive function. When you're dealing with trees, you'll see quite a bit of recursion. So to print in order, let's see. In order, we visit the left, then the parent, and then the right. So visit, then so go left, then print, then to the right stuff. So to do this, you will call the same function. So print in order. You will, this will take a root. I forgot about that. So you'll take a root. First condition, base condition is just making sure the root has something there, so it's not none. So you can just say if root, and everything can be nested inside. So you want to visit the left part. So in order, we visit left, then parent, then the right. So root dot left. Then we can print the parent, which is the current root that we're at. So we can print root dot value. Some people call it like we're visiting the node. We're actually like accessing the value there. And then you can print the same thing. So print in order, oops, for the right side. Yeah, get that right. Okay, so if I say here, print in order, and I send in my tree root, it should traverse the entire tree and show me all the values in order if I did the insertion correctly. So let's see. And it did. So 20, 30, 40, 50, 60, 70, 80. Awesome. And you see here, when we inserted them, they were not in order when we were inserting. So the tree ended up being built correctly. Question about the traversal or the insertion. Is this making sense?
Yeah, can you scroll down to the very bottom? How you, what was the first thing you initiated with? You just tree root equals none. So does that have to be the first step for it to be? Does it have to be the first step?
For this one, no. So you can just say tree equal insert, and you can just send in none because we didn't start off with anything.
Oh, okay.
Yeah, so you can do either. Another option is if you don't want to send in anything for the first one, you could set a default for this. But yeah. would have to set for both of them.
I think I missed this. I think this is a basic question, but I apologize. How is it? How is it basically traversing and going through everything and printing that out and not just that first set of 3 nodes, the parent, the left and the right?
Yeah, so that's the beautiful power of recursion. So let's look at this one. So, okay, maybe I'll do the numbers. Oh, I'll make the numbers match here. So we inserted 50. 50 ended up here. So 50, then 30 goes over here. This is when we were inserting. So 20 will go on the left side. 40 will go over here. 70 will end up here. 60 will go over here. And then 80 goes over here. Okay, so when we were inserting the nodes, this is how the tree ended up. So our code calls this function with the left subtree. So let's say we're starting off here. So we're starting off at 50. We get to the first line, we get to line 54. It says to call this function again with the left node. So now the function gets called again. We're in print in order with the root being 30. So this is our root. Our root is 30. We get to line 54 again. We want to explore the leftmost. So now in our new call, this is our line. So we get to 20, we get to 54 again. We're going to send in root.left. So left is going to be null when we call it the fourth time or third time, I lost track. So when it gets to here and this is null, this doesn't execute, so it returns. So when it returns to back to the point in the recursion where this one was the root. So it basically, this one finished executing. Now it's time to print. It prints the value that it's at, and then it prints anything on its right, which there isn't anything, and then it returns. So when it returns, the last node or the last root it was at was this one. So the line 54 had already executed when we were at this one. So now all there's left to do is to print. So it's going to print 30, and then it's going to go to the right side of it and send 40 into the function again. And now our new root is 40. It will go through here. There's nothing to the left of it. So this will return. This will actually print out 40. And then the right side, there's nothing on there either. So this will return. So now we finished executing here. We went back to 30. We had just, when we were at 30, we just finished executing our right side, right? Because 40 is on the right side of the 30 node. And so that returns. And now we're back to 50. So this is our first recursive call that we called. This is the main tree node. So now here we printed out all the left side. We already went to the left side of this node. Now we are going to print out 50. So 50 prints out next. It then calls the function again with the right side. And it does the exact same thing for the right side. So here it checks the left side first. It'll print out the leftmost value. Then it'll return, it'll print out the right, or it'll print out the value of the root itself. Then it will go to the left side and print out the value of the node. After it goes like left and right. So
Gotcha.
yeah, so going left first, because our leftmost value is the smallest, it'll end up, so when you put the print statement in the middle, that makes it in order. And it kind of helps you remember how to write this code, because when it's in order, the print statement is between the left and the right. So based on this, if I told you so these 3 lines are basically going to be the same for all of these, you're just gonna like change the order of them. So this, gonna send in the root. And this will also take in a root and do a similar thing. So for these ones, we're gonna have to change it up a little bit. But yeah, so in order, you go to the left, all the way to the left as you can go. You will print the node, and then you'll start printing as you keep going up. So you'll print, then go back, print, go to the right, print, and then go back up, print.
Cool.
Yeah.
My dumb eyes just didn't see like the underscore in order to realize that it was like another function call for it to be recursion.
I see. Okay. Yeah.
So I guess one additional question based on, so once it finishes that left side of the tree, it gets back up to the root of 50.
Mhm.
And then you said, okay, well, we already ran against the left side of the tree, so we're automatically going to go into the right. Maybe this is getting into the weeds, but is like the call stack smart enough to realize like, okay, we've already done the left side, like we already have a stack of
So
things. Go ahead.
yeah, I don't know what's the best way to visualize this? Let's see. So let's say we start off at node 50. There are going to be, is there a table here that I can draw? So let's say this is stupid. Okay. Which number 6? Okay, cool. So if I do this, then I draw this way. Okay, so for each of the for each node, there's 3 commands that it needs to execute. So we're gonna walk through them real quick. Okay. So this one is visit left. Print val. And then we are going to visit right. Okay. This is an ugly table, but bear with me. Okay. So doesn't matter. You guys can see it, but you can see both. Okay, so we start off, the root is 50. So we visit left. When visit left happens, we then visit left. This is a bad way of doing this, huh? So when we visit left, it makes another call. Yeah, so these are all the operations, these are all the function calls. So here, root equals 50. A root is pointing to the node with 50. Okay, so how do I hide this? Don't think I can. Okay, so we start off with the root equals 50. When we visit the left here, nothing is really in this value yet. So because we make another function call. So this function call, it gets called with root.left. Root.left is 30. So here, root, so I'm just going to write 30 here. So 30, then it goes to visit left. There is a left, so it doesn't have anything yet. So it calls again to root.left. So 30 is the root, 30.left is 20. So it makes another call with 20. And when it gets to 20, it then does print in order again with the left. This one sent in, this one did none, right? So it made a call with root as none. So this one was also nothing yet. So when it was none, it gets to the if statement over here, right here, asking if it's root. So this returns, right? So this is done, it collapses. Now we're back to 20. This has finished. This is now done. It goes to print val, which is the next execution, the next point of execution. It prints out 20, and then it visits the right. So 20 to the right, it adds another none, and then it comes back. So this is, I'm just going to put an X here, and then it's done. So when this finishes, so this entire row finishes, it collapses, right? This now returns. So we've already done this stuff, so I'm going to delete it. Then we are back to 30. 30 had only executed visit left. Visit left is now done. Oops. How do I go back? Okay. So yeah, visit left is now done. We are going to print out 30. So I can just start here. So 20 printed out and then 30, right? And then we're going to visit the right side. So the node that we're starting at is 30. The right side is going to be 40. So here, this is just a function call, right? This becomes 40. This is a new function call with the root as 40 here. It visits left, returns nothing, right? It then prints the value of 40. So this now is added to our list here. And then it visits the right of 40. There's nothing really there. So it returns, it collapses. So all of this returns. We're not using it anymore. And so this one returns. So this is done executing here. Sorry. Okay. So yeah, so 40 is done. It finishes. I'm not good at this tool yet, as you guys can tell. Okay. So we finished 30. All of it is done. It collapses back. We're back to when the root was 50. We had only visited the left side. So now we print out the value and then we visit the right side. And then we keep adding on to the call stack as we go.
Gotcha. Okay. So it's like that root, the root call in the call stack, we're still at 50. We just collapsed everything leading up to it. We're still at 50, and then we have to address the other side. That makes sense. Thank you.
Exactly. Yeah. So the initial call is still hung up. It's still waiting on everything else to return. Yeah.
Right. Gotcha. Thanks.
Of course. More questions?
So in line 54, so line 55 won't be executed until you finish line 54. And
Line 50, yeah. So when line 54 comes back, then line 55 will happen. Yeah.
okay, so line 55 won't be executed until you finish recursive function,
Mhm.
then call the 55, then 56. Is that
Exactly.
okay?
Yeah.
Sweet.
Yeah. Other questions? They can be as small or as big as you want. No? Okay. So yeah, that was That was in order traversal, so it will, if for a binary search tree, it will print everything out in order. It's a good way to check that your insert was done correctly. So when we want to do pre-order, based on what I said about this, where we're printing in order, so in the middle between the things, pre-order, if we want to visit the parent first and then the left and then the right, how would we do that? What would we have to swap around?
Well, you just change the order there. Do the value first.
Yeah, so we are going to literally just print the value first. So in theory, with the pre-order, we visit the parent, then the left and then the right. So it will print 50, and then it will go and print 30, and then print 20, then 40. Then it will print, I think 70, 60, and 80. So let's put our predictions here real quick. So I said, what, 50? Do you guys think this makes sense? So 50, 30, 20, 40. And then 70, 60, then 80. Okay, let's see if we print pre-order. Let's see. So it did 50, then 20. Oh, does someone know what I did wrong? Do you see it here? In the pre-order function.
You have no
You're calling
value.
the in order function.
I am calling the in order
Yeah.
function, exactly. So I'm doing recursion wrong. Okay, these are pre-order. Let's see now if our predictions are correct. And it seems like it is. So 50, 30, 20, 40, 70, 60, and then 80. So it basically visits the root first, and then it traverses and keeps doing that. So visits this one first, and then this one, and then this one, and then this one, and so on. And the last one, post order, will go all the way, print 20, and then 40, and then 30. So let's do a prediction is here. What would be next? So give me the numbers that you think it would do it. If we're going left, then right, and then printing. So we start at 20.
Yeah, it'd be like 20, 40, 30,
Okay, 20, 40, 30.
then up to 50, right? No, sorry, then 70, 50.
Then 70, 50.
No, wait. No. Because you're jumping. So after you do left, right, top, that resolves. So then it goes to the right. Oh, so then I think 60, 80, 70. Right? Or
Let's try it out. 60, 80, 70,
then
50.
50 at the end, top last.
Let's do it. And then for post order, we print after, and I just need to make sure that I'm actually calling the right function this time. Okay, post order, then we run it. See, I didn't change the function call. Hold on. Post order, then we run. Let's see, 20, 40, 30, 60, 80, 70, 50. Yeah, you got it right.
Nailed it.
Awesome. So basically it prints the root after at the end. Questions on this? No? Are trees a little more digestible now? You kind of understanding the traversal of it. Yeah. Okay.
Yeah,
Um,
this made way more sense. And like even the recursion part is clear now than the prior lectures that we've had so far.
I'm glad. Thank you. Yeah. I did quite a bit of research. But so this is the basic traversal that happens with most trees. So this is something that you might see. Okay. How much time do we have? We have about 30 minutes. Do you guys want like a 5-minute break? Yeah. Let's come back in 5 minutes. Okay. I'll be here if anyone has any questions.
Can you scroll up to where it says insert? I kind of want to see that function again.
This one?
Thank you.
Yeah, I'll remove this. Just put it up here. And there we go. Okay.
So would it reach line 35 or would it stop at 33
For which one?
for the insert?
Uh-huh.
Would it, so we have if and then else, and then within the else, we have nested if, elif, else.
Mhm.
And then we have like a last one, the root node. So it has to, so it goes back to that. Oh,
For this one, you mean?
yes.
Yeah. Yeah, so basically in the beginning, we have our root and we are modifying the right or the left based on the insertion. And then we're just returning that same tree. So basically we take in the tree, we modify it, and then we return the same tree. That's what's happening here. So root of the tree, if we're modifying the right side or we're modifying the left side, we do that, and then we return the same tree, the same root that was sent in.
Okay, thank you.
So line 32 and 33, we technically don't need that.
Let's test it out.
It'll
'Cause
it'll
we
return
had it
at
in
35
there.
anyway.
Sorry?
Because it'll return at 35 anyway.
Yeah. See if. So that was for catching duplicates, basically. So let's do, I'll try to insert 50 again. And we'll see what happens. And then we'll do an in order traversal. So 20, 30, 40, 50, 60, 70, 80. It seems like it didn't really modify anything. If I want to check what it actually did, I can just run it in the debugger real quick too. That might have been actually a good way to see this. Maybe when everyone's back, we'll do that. So this is the first one, inserting 420, hold on. 30, 20, and then the 50s again. So now the value is 50. It did get, yeah, it came down here and then it returned root. But like you said, we don't really need it because if it doesn't go in here, it's going to return root anyways. So yeah, it's just extra code that doesn't really do anything special. Awesome.
I mean, so a question, and it's kind of more maybe like a industry question or a standards question, but
Mhm.
yeah, that line was extra, but I mean, it made it pretty readable too. I mean, is that something where like out in the real world, they're going to be like, oh, take it's 2 extra lines, what are you doing? Whatever, right? Because
Mm,
on some level, if it's more readable in that contents, like it doesn't hurt anything.
yeah, that is true. I'm actually not sure. I think with a lot of these like industry standards, it comes down to people's preferences and how strongly they feel about these preferences. There are some like common ones that everyone's like, yeah, this makes sense, so we'll all do it. But then there's some people that are more nitpicky about certain things. So I would say if you think that it helps you in your code, just add it. It's not like the extra 2 lines won't really hurt. I know probably some people would be like, oh no, but if it's not doing anything, then why is it there?
Yeah.
Yeah.
I mean,
So
I guess they just won't pull it or merge it if
Yeah.
they don't like it.
it's just for you, your code.
Yeah.
Yeah. Or you can add comments. I think comments is it's like a good middle to reach there. Awesome.
Hey, Zainab.
Yeah.
Can I ask a question about the call stack and maybe like how to emulate that on like a regular stack? Because I was trying to do that earlier
Mhm.
and I was having trouble figuring out how to use a while loop and then just having an array as
Mhm.
a stack and then pushing whatever nodes I'm on. It's
Okay.
basically the same thing as recursion, right? But it doesn't, I don't know how to loop through it, I guess. Would you be able to explain that real quick?
Sure. What are you trying to do? So let's try to.
Rather than using recursion
Uh-huh.
to, is it possible to just have an array, like call it a stack, and then use a while loop so that while the length of that array is greater than 0, essentially visit a depth first search traversal of the tree and then push the left and then the right to the stack and then I guess go through it that way. Is that?
Yeah, let's try it. So basically we're taking in a root and we have a stack that we're going to hold on to the values of, right? Or the values of the nodes. Okay. Or is it the nodes themselves?
Either or.
Okay. So let's say we start off with our root. So if there is a root, then we say stack append. And this will be, what is it called? Yeah, I'm just gonna do the values, root dot value. And then, you said you're not doing it recursively, you wanted to do it in a while loop, so while,
Yeah, that's what I was wondering about. Is it like while stack, the length of stack is greater than 0? But at one point you would have to append to that the root dot left and root dot right, wouldn't you? So you know to visit those afterwards. So this is where I'm getting tripped up on.
yeah, so let's do, let's start with a current node, because that's typically how you like want to traverse through trees and stuff. So while current is not null, then we can say, we can have this in here probably, so we can remove that. So we start at the root, we append, then we do current, but we have to visit both. So we might need a visited and an unvisited stack. I think that might be helpful. So unvisited and then visited. So we can start off by appending to unvisited and root value. We can also say if root dot, oops, root dot left, then we can say unvisited dot append root dot left. Okay, so we append the root value, we append left and the right values. We might want to make this a queue instead of a stack. But it doesn't matter as long as we like visit one. So maybe this stuff can be inside here. I'm gonna remove this stuff. Do we need this? So I'm assuming like current dot value and then current. So when we visit it, we can maybe put the value in there. So unvisited, we append this. Then, like you were saying, if hold on, sorry, I'm confusing it a little bit, but I'm also trying to think through it. So let's say if it's unvisited, we append the node that we want to visit. And yeah, so this would make sense here. So while unvisited is length of unvisited is greater than 0. So while there is something that's there that we need to visit, we then can say visited equals, dot append the root value. Then we check for the left. If there is a left to this root, I'm not going to call it root, I'm actually going to call it current now. No, sorry. Okay. So basically we start at the root. We say while there is something to visit, so unvisited is just gonna hold on to the data that we want to, or the nodes that we want to visit. We get in here, we pop the value, so we can do unvisited dot pop. We will remove first thing that we want to see. We can hold on to it, we can also not. So turn that left.
I think I'm following. So
Yeah.
when you pop whatever current is, you would just set current to whatever was popped from
Mhm.
unvisited, and then I guess push that value over to the visited array, right?
Mhm.
Until you hit, and then at a certain point you would have to append to unvisited current dot left and then current dot right,
Mhm.
and then eventually just set current to each unvisited value until it hits null. and then I
Yeah.
guess push those values to visited. Okay, I think I follow.
Yeah, I don't think we even need to hold on to current. We can just start with the node. So basically, we had the root, we appended it to unvisited. We pull it out because that's the node that we're currently actively visiting. So node.value will append it, and then we'll check its left and its right. And if they are there, we can add them to the unvisited list to then visit them afterwards. And then
Yes.
yeah.
Got it. Thank you.
Yeah, let's see if this actually works. We wanted to, let's print out the visited. I don't know if the order is going to be correct. For these, just because of the order that we did them in. Oh, I didn't call the function. Hold on. Keep doing this. What did I call it? Loop through tree root.
Yeah, I think it would just go start at the root and then start. Yeah.
That's cool. So it added them. If we look back at our little diagram here, it went, oops, 50, 70, 80, and then 60, 30, 40, 20. Cool, yeah. And do you know why it went that way versus another way? Like which operation actually made it do that?
Is it because of the order that we appended it to the unvisited array?
Yeah, it's the order that we appended it, also the order that we pulled it from. So because we used the stack, we put 50 on, and then we pulled that off, we put both 30 and 70. 70 was the top one, since we're popping off the top, we then took. So if we wanted to go to the right instead of the left, we would use unvisited as a queue instead of a stack. So if we got dot, I think it's not get, what was it? Dot,
At 0 or whatever.
yeah, we can remove the value. Does it return anything? No, returns none. Yeah, but basically this one at 0. And then
I think you could call pop and give it an index.
oh yes, thank you. I forgot about that. So dot pop with 0. So if we're pulling from the bottom, so we basically just made this a queue. If we print it out again, it will go 50, then 30, and 70. And then, so this is actually perfect. I'm glad you asked this question. This is breadth first search. This is how you actually implement breadth first search. You push everything to, you start pushing stuff to a queue. So the unvisited queue, you push these nodes, and then as you're looping through and you're pulling them out, it ends up visiting everything one level at a time. So 50, and then 30, 70, and then this last level here. Yeah. Awesome. I'm glad you asked that question. That was, I got to show you guys that. We don't have too much time. Any questions about what we saw today or further things? I just want to mention remove, since we've only really done inserts. So search is going to, the traversal is going to be pretty similar to when you're inserting. So you're just going left or right, and then when you find the value, you return true. If you don't return, if you don't find it at the end, just return false. So the search is pretty self-explanatory. I would recommend playing around with it. For the remove, however, there are a few cases that you have to consider. So when you're trying to remove, first, here, let me just write these out. So here are some of the cases that you might run into. First case, empty tree. This is always there. So you're trying to remove from something that doesn't have anything. Second is not empty tree. I guess that's obvious. But within that, we have a few cases. So if the tree is not empty, so let's say we have this stuff and we want to remove 20. So 20 is one case. Let's say a tree that looks like this. So one case is empty. Obviously, we just talked about that. One case is, let's say, removing this one. One case is removing this one. And one case is removing this one. Oops, that wasn't drawing anymore. That and that. So can you tell me what the difference is between these three? What are the three cases here?
One has 2 child nodes.
Mhm.
One has 1 child node,
Mhm.
and one has no child nodes.
Exactly. One child. And no children, yeah, for sure. So these are the three cases that you would have to accommodate for. And we don't have enough time to implement the entire thing, but I'm going to show you some resources that will help you actually like use it as a, you can use it as your starting point when you're trying to implement these things. So do this. I'm going to look up BST remove node icon. That works. So I personally like some of the Geeks for Geeks explanations. They have pretty good explanations for things and good diagrams. So it kind of goes through all the steps. So node to be deleted is a leaf. I forgot to mention this. So if it's if the node is at the end, so if it's like just this, it's not connected to anything below it, it's called a leaf. So a leaf is a node with no children. So if the node to be deleted is a leaf, then you simply remove it from the tree. If the node to be deleted has only one child, then you copy the child to that node and then delete the node. So they give you like the pseudocode basically of the thing, and then they also go through how to implement it. When you're trying to learn things like this, I highly, highly recommend you read from the top and you just actually read through the pseudocode, draw it out, understand it, and then go to the code. Don't go to the code immediately and try to parse it out, because sometimes it will confuse you a little more, especially if there's like recursion and like different things happening in different places. Start off always with the pseudocode, understand what are my different cases for this thing? What am I trying to build? What am I trying to solve for? So yeah, this one, there is a, so if you scroll down here, delete a node from BST, so Geeks for Geeks also has their own problems like leak code. So if you are interested in doing these are also recommended. They have this like similar to leak code where you can run it and stuff like that. If you don't care about their point system and you want to actually see like the breakdown of what the problem is or understanding it, they have an editorial part where they kind of like go over the thing. It's very similar to their actual page of explanation. and then there's an actual solution. But yeah, I just want to help you navigate these sources a little more. Also, you guys wanted to see a little bit more about AVL trees. AVL tree. There's a few. I'm going to go back to here. So AVL tree again is a binary search tree that is balanced. So the difference in heights in certain nodes is not more than 1. So this one is at most 2, this one's at most 1. So the difference between this node and this node is 1. So the height, this is height of 2, this is height of 1. Yeah, so basically every leaf, or like the end, starts at 0. So this is height 0, height 1, height 2. It takes the highest of the 2 lengths of subtrees basically. And yeah, so it keeps track of like that. This is not an AVL tree because you can see it's more heavily weighted on one side. So yeah, AVL trees ensure that your yeah, so most of the operations take O of H. H is the height of the tree. So these are pretty optimal. And so it, like I said, like I mentioned this morning, it could become O of N if your binary tree is very skewed towards one direction. So it's not optimal anymore. It's not worth it. So yeah, with insertions, you have a few different types of rotation. So you basically insert regularly, and then as you're going back up the recursive call stack, you're checking for heights. And when you identify that a height is out of order, then you will need to do certain rotations, and there are 4 possible arrangements for the rotations. So basically, so let me explain what these values. So basically, your node to insert is W. You insert W, and then you're walking up to find the first unbalanced node. The Z is the first unbalanced node. Y is the child of Z that comes on the path to W. So basically, Y needs to be moved around as well as Z. So Y is the left child of Z. And so, yeah, I won't go into too much detail, but basically there are 4 different cases, one of them where you need to rotate this way, one of them need to rotate this way. And yeah, there's illustrations as well of all the rotations. Yeah, questions? I know this stuff is a little too advanced, you don't really have to care about it, but if people are interested, it's good to know.
I think I was the only one who asked about AVLs, but thank you.
Did
Appreciate
it help? Or
It did help. No, I know. I'll go to this resource actually.
Yeah,
read up on
awesome.
it.
Yeah. Yeah, after this entire course is done, and you want to, if you're interested in getting into more data structure stuff, I would recommend just learning from these things, like these resources. And if you feel like you've mastered like trees and linked lists, I would recommend going to graphs next. Graphs are very powerful. It's a lot, so we can't really get into it now, but they're a special type of tree, where a tree is a special type of graph. It's one or the other, but it has a lot of real world applications, and some algorithms that you will hear about on the course of your learning journey are like Dijkstra's algorithm. That's a pretty big one. So Dijkstra's algorithm is finding a shortest path between two nodes. So it's like I said, I think a few days ago, it's used in like map searches, like finding there's a problem in computer science called the traveling salesman problem. Basically, there's a bunch of cities and all these cities are connected to other cities, and you have to find and each connection is weighted. So each one has like a distance or something like that. And you want to try to find the shortest path. And there are ways to traverse graphs in a good way that actually get you to a good result quickly. And you don't have to like try to see all the different paths, because that would take forever if you have a big set. Yeah. Any other questions?
Just kind of going off of graphs, are those like geared towards like operations research problems, or just, 'cause I think I've heard of the traveling salesman back in OR.
Yeah, it has I don't know specifically if it's operations, but research in general, a lot of different realms of research use it, especially like AI and search and knowledge graphs and all the fun stuff.
Can you go back to the first tree that we drew out? I just wanna like look at it really fast.
Here? Or,
Yeah,
yeah,
that was it, yeah.
perfect.
Thank you. Just like a small little screenshot of it, just like so I can work with the problem and look at it.
Yeah, definitely. Here, this. Here, if you guys want the link. I don't know how this works exactly. If you send someone a link, oh, actually, that link might not actually work. Hold on. I have to share it. Export. Oh, this is just an actual image. Okay. I'll send this image in Slack, but I want to also do the live version. Oh, Leo, I just saw your message. Yeah, you used it to solve maze puzzles. Yeah. Graphs are cool. Graphs are, yeah, definitely used in AI. But yeah, I gave you guys access to this, so if you want to copy it or do whatever, take screenshots, feel free. Okay, any last questions?